Okay, here's kind of a step-by-step way for using the binomial formula. First thing you have to do is identify what a success is. Now keep in mind it doesn't have to be a good thing. So depending on what the problem is and how it's phrased, a success might actually be a very negative outcome. So make sure you are very clear of what a success is for your particular problem. Next thing, determine P. That's your probability of a success. Then determine N. That's your number of trials. Determine X. That's the number of specific successes you want. And then we're going to use the formula. So if you look at page 231, example 5.2, they've got the mortality example here again, but we're going to do it using our formula instead of going through that chart. So if we identify what a success is, that was being alive. Our probability of success, well, P was equal to 0.8. Our number of trials, we had 3 people that we were interested, so N is equal to 3. And now our number of successes is, we're going to have to fill in our table for that. Okay, so 0 people alive, 1, 2, or 3. So now when I look at my formula here, I don't need to go back there. We're going to go ahead and just start filling in the blanks. So for 0 people, we would have 3 choose 0 times the probability, so 0.8 raised to the 0 because that's how many I'm interested in, and then times 0.2 raised to the x minus 0. Well, 3 minus 0 gives me 3. So when I calculate that out, I should end up getting the exact same probability that I got before of 0.008. So the probability of 0 people being alive is 0.008. If we fill in for 1, I have 3 people to pick from. I want to know that exactly 1 is alive. My chance of the success is 0.8, and I want 1 success because I want 1 alive. And then my chance of failure is 0.2, and 3 minus 1 gives me 2. So I have 1 success and 2 failures. When we calculate that one out, you should get 0.096. Okay, then when I go for 2, I would have 3 choose 2, so I do my combination. 0.8 is my success. Well, I want 2 of those. 0.2 is my failure. 3 minus 2 is 1. So I have 2 successes, 1 failure. Calculate that out, and we get 0.384. And then my last one, 3 people being alive. Well, I have 3 to pick from, and I want 3 successes. My probability of success is 0.8, and I want 3 successes. My probability of the failure is 0.2, and I want 0 of those. Calculate that out, and you get 0.512. So see how we can come up with these probabilities much faster by using the formula as opposed to having to list all of the outcomes and then calculate their individual probabilities. Okay, now binomial distributions. They can have different shapes. They can be symmetrical or they can be skewed. On page 233, they give you 3 different graphs to illustrate this. The first graph, the green one, would be considered right skewed because the data kind of trails off to the right. The middle one, that peach one, would be symmetrical. And then the purple one would be left skewed because the tail trails off to the left. Now if you look underneath each one, they tell you what the probability of success is. So for that green one, that first one, they tell you the probability of success is 0.25. And what that does to it is it makes it right skewed. So it shifts your data, like the bulk of your data, farther to the left. And it's because your probability is less than half. On the middle one, your probability is exactly half, so you're going to have a perfectly symmetrical graph. Now, when your graph is right skewed, your probability of a success is going to be bigger than a half. And if you think about what that means in terms of the last example we just did here, our probability of success was 0.8. So logically, you're going to expect more people to be alive than dead, because you have a 0.8 chance of being alive compared to dead. So if you look at across the bottom, you have 0 people alive, 1, 2, and 3. You're going to expect most of your probability to be up here with the 2 or 3, because you have a better chance of being alive. It's not a very good chance that 0 people are going to be alive, so that's going to give us that type of a graph, which would make it left skewed. Okay, the mean. Since this is a discrete random variable, you can use that same formula we had before, but when we have a binomial distribution, that formula actually will simplify down into mu equals n times p. So this is a much nicer formula to use. If we use that mortality example, our n was 3, our probability of success was 0.8, so our mean ends up being 2.4. So what that tells us is that, you know what, we would expect 2.4 people to be alive when they're 65. Standard deviation works a similar type of way. We can still use that formula that we had before for discrete random variables, or since we have a binomial distribution, we have a formula that's a little bit more simple. We can take our n times p times 1 minus p and take the square root of that. So for our example, we would have the square root of 3 times 0.8, because we had 3 trials, our probability of success was 0.8, times 1 minus 0.8 would give us 0.2. So that formula will also give us the standard deviation. If you look at page 234, they go through this exact thing right here, and then I'm just going to cheat, and they calculate that out to be 0.69. So on average, our data points are 0.69 people away from our mean. Okay, that takes us through all of Chapter 5. Go ahead and do what you can do on the syllabus, the Chapter 5 assignment, and we will see you next Wednesday.